Hello and welcome to this online open day from the Department of Physics and Astronomy at UCL. My name is Phil Jones and I am Professor of Physics at UCL and also the department's undergraduate admissions tutor. In this short presentation, I'm going to give you a brief introduction to UCL and the Department of Physics and Astronomy, the subjects we teach, and what you can expect to learn should you choose to join us at UCL. Let's start with a short history of the university. UCL has its origins with the original London University, founded in 1826. Although our most famous founder is probably Jeremy Bentham, whose auto icon you can still see today in the new Student Centre, also influential in our founding was this man, Lord Henry Brougham, a lawyer, a Member of Parliament, a campaigner for the abolition of slavery, and also, although the term was not used at the time, a physicist. One of the founding principles of UCL was that it was open to all, irrespective of their religion. Shortly after the university was founded, the first professors were appointed, including one in natural philosophy and astronomy, making us the first university in the country to include astronomy in the name of a department. We became known as UCL following the creation of a federal University of London, initially with King's College. And in 1878 we were the first university to admit women as students on equal terms with men. At the beginning of the 20th century, the University of London expanded to include Queen Mary, Royal Holloway, and other London colleges, an arrangement which lasted nearly 100 years, until at the beginning of this century, UCL obtained its own degree awarding powers, and our students now graduate with a degree certificate from UCL. So as I mentioned, the department has its origins at the very beginning of the university, and here you can see the first head of the department, the Reverend Dr. Dionysius Lardner. Something of which I think the department can be extremely proud is that in 1832, Miss Potter and Mrs. Rogers took a course in electromagnetism in the department, making them the first female students in any department in any university in the country. We can count a number of famous scientists among our alumni, including 3 Nobel Prize winners, William Bragg, Owen Richardson, and Francis Crick. After a number of name changes throughout its history, the department became known as Physics and Astronomy in 1950 and has grown steadily, such that now, in 2020, we are one of the largest and most successful physics departments in the UK. And here you can see who the members of the department are. We have nearly 600 undergraduate students, about 250 postgraduate students, including both taught master's students and PhD students, over 100 postdoctoral research staff, and over 100 permanent academic staff. We are also a diverse department. Around 1/4 of our undergraduate students are female, and our students come from all over the world, a little over 40% from the UK, about 15% from the European Union, and just over 40% from the rest of the world. So what can you study in the department? Well, we offer 6 degree programs, that is 3 subjects, physics, astrophysics, and theoretical physics, each of which is either a 3-year degree leading to a BSc or a 4-year degree leading to an MSc. You can see them here, listed along with their UCAS codes. Now, many prospective students will first ask what is the difference between the BSc and the MSc. The 4th year of the MSc version of the degree is a preparation for further study, a research degree, and it includes a significant amount of project work carried out in one of the department's research groups. Many students will choose the MSc degree because they have decided at an early stage that they are very interested in a career in research. We're now seeing that many students will choose the 3-year BSc degree and follow this with the 1-year taught master's degree, an MSc, which may be in physics, perhaps a more specialised part like high-energy physics or biophysics, maybe in a related subject like high-performance computing, or maybe in something completely different like financial management. Our advice is that if you are unsure, to choose the 4-year MSc degree, as this enables you to have all your financial arrangements like your student loan in place for 4 years should you need it. It is possible to change between the BSc and the MSc up until the end of your 2nd year. You can even change between the different subjects, physics, astrophysics or theoretical physics, from when you receive your offer up until the end of the 1st term, after which the course contents start to diverge. The only caution here is that theoretical physics has a slightly higher entrance requirement, which you must meet in order to change onto the programme. And let's have a look at what the entrance requirements are. For the physics and astrophysics programs, we require 3 A's at A-level, including maths and, of course, physics. If you are studying the IB, the headline figure is 38 points, with a total of 18 points in 3 high-level subjects, including maths and physics at grade 6. For theoretical physics, the entry requirement is slightly higher at A** AA, including both maths and physics, with the A* in one of those subjects. We do prefer students to have further maths, since theoretical physics is a very mathematical subject, but it is not compulsory, as we know that not everyone has the opportunity to study it. For IB students, we require 39 points with grades 7 and 6 in maths and physics, in any order. Now let's have a look at the content of a degree. As an example, here is the structure of the 4-year MSci Physics degree programme. If you attend some other university open days, you'll probably find that the beginning of the physics degrees in years 1 and 2 look rather similar. This is because there is a core of knowledge that physicists think that physicists need to know. Classical mechanics, waves and optics, thermodynamics, electromagnetism and so on. Also, you will notice a lot of mathematics at the start of the course, 2 modules in the first year and another in the second. Although further maths is nice to have, we do teach in these modules the maths required for the rest of the degree. You will also see that experimentation is an important part, as is computing, and from very early on we teach our students programming in Python. At the bottom you will see 2 additional non-credit bearing modules in communication skills. Graduate employers tell us that the skills that they value in graduates include numeracy, teamworking and problem solving, all of which you can acquire in a physics degree, but also good communication skills, and so these modules aim to help our students develop these right from the beginning. As the course progresses, you will see that there is more space in the timetable for options, modules that you can choose that reflect your particular interests. It is here you will find that universities differ, as the modules offered as options in the 3rd and 4th years will reflect the research of the departments. Here is one of UCL's great advantages. As we have a large department with diverse interests, we are able to offer a wide range of optional courses with content at the leading edge of the subject. If we look at the options available through the degree, you will see that this grows from choosing 1 from an available 3 in year 2 up to choosing 5 modules in year 4. This means that in the final year of your course you choose the entire content around the areas of physics that interest you most, your research project and 5 lecture modules. UCL is able to offer the range of options taught to great depths because the academics delivering these modules are also performing cutting-edge research in these subjects. UCL is fortunate to have some excellent teaching facilities with access to larger lecture theatres, 3 teaching laboratories that have recently undergone a multi-million-pound refurbishment, and of particular interest to the astronomers, the UCL Observatory in Mill Hill, North London, where the new 80cm Perrin telescope was installed last year and is now available for undergraduate observing. Of course, in the next academic year, we anticipate that some of our teaching activities may not be able to take place in their traditional form, so we are adopting a blended learning approach, utilising learning technologies for remote teaching where necessary. And now a few other highlights from the department. A few years ago, some of our astrophysics undergraduates were engaged in their regular observing session at the observatory when they noticed in the sky a bright object that had not been there previously. This turned out to be a Type 1 supernova and the closest of its type to Earth to be observed for several decades. If you are interested in particle physics, you might like to follow our former head of department, Professor John Butterworth, who works at CERN on the Atlas experiment, who tweets regularly about physics and also maintains a fascinating and informative blog called Life and Physics. Our current head of department is Professor Raman Prinja, pictured here. Not only is Raman an active astronomer and the head of the department, he somehow finds time to be a highly successful author of popular science books. His latest book, Planetarium, won both the American Institute of Physics Science Communication Award and the Royal Society Young People's Book Prizes for 2019. Our students are also very active. Alongside their studies, many of them are involved in the UCL Physics Society, who arrange many extracurricular activities for students, some academic related, such as guest lectures or careers advice, as well as social events. You can find out more about the Physics Society from their own webpage and their social media. UCL as a whole is committed to equality and diversity, and the Women in Physics group plays an important part in this mission by supporting, representing and celebrating the achievements of women in the department. You can find out more about their work from their website here, or by contacting Abby Bray at the email address shown. I have mentioned a few times the research activity of the department and how it informs our teaching. Research in the department is organised into the 5 thematic areas shown here, ranging from the physics of gravitational waves to the physics of virus entry into cells. We also collaborate closely with a number of other national research institutes, and in the latest Research Excellence Framework, or REF, in 2014, UCL was rated #1 in the country for its research strength. And that concludes this presentation about our undergraduate degrees. You can find out more about our degree programs at the link shown here or on social media using the UCL Physics 2021 hashtag. If you do have any questions, then myself and some current students and staff will be here at the end of the presentation to try to answer them, or you can send us an email at the address shown here. But before that, we have something of a treat. You undoubtedly saw the astonishing first ever images of a black hole that were published last year. This image won the team that produced it the Breakthrough Prize in Fundamental Physics, and earlier this year the discovery was even featured on a stamp. Dr. Ziri Younsi was a part of the team that acquired this image, and he is based at UCL's Mullard Space Science Laboratory. So I'm going to hand over to Ziri now, who will tell you a little about black holes and how this image was obtained, and I'll be back after his talk to answer any questions about our degrees and admissions.
Good afternoon, everybody. My name is Ziri Younsi. I'm an astrophysicist working here at University College London, and today's talk will be about the first image of a black hole and how we actually produce this. So I used to work within a project called the Black Hole Cam or Camera project. It's the bottom left logo here. This was a ERC, European Research Council, Synergy Grant funded project whose aim was to take the first ever picture of a black hole. So this was a few years ago that I joined this project. So my background actually is I did my graduate and postgraduate studies here at UCL. And it was actually the training I received, and my thesis itself, my PhD thesis, was on this very topic that enabled me to join this project 5 years ago now and work with leading scientists in Europe on techniques to image a black hole, both from an observational perspective and from a theoretical perspective. And after a year, we ended up joining a project called the Event Horizon Telescope, or the EHT, and this project was effectively the collaboration which imaged the first ever black hole, which we'll talk about in a moment. And so this image that you see on this first slide is a computer simulation that I ran of a black hole at a certain inclination angle. And in today's talk, I hope to convey to you some sort of feeling and idea about what's going on and what these images mean. So let's jump straight in. So this is it. This is the first ever image of a black hole. And this image was taken by the Event Horizon Telescope collaboration, published on the 10th of April 2019, so just last year. And it, I think, would be fair to say that it was a highly successful piece of scientific publication, both from a theoretical, from a sort of scientific perspective, but also from a sort of public outreach and engagement perspective. It was on the front covers of almost every newspaper of that day globally. This is just a small selection. And so I think it enjoyed some success. But one of the big things which remained, I think, for everybody was, what does this mean? And so as scientists, we tend to have to work very hard to understand what this means. What does this image mean? What can it tell us? What do we learn about black holes and about their place in the universe? But of course, social media was very quick to provide some interpretation. So I'll list just a few interpretations here. I chose my favorite three. So the first is fear. So, you know, Eye of Sauron and all the rest of it. So in a sense that these images sort of reflect the sort of fundamental tenets of human nature. So we have fear, we have food, and my favorite, felines. So people have discovered the giant cosmic kitty cat, and it looks like there are two black holes, but there we go. So social media was quick, but as scientists, I think this really tells us that a lot of people are wanting to know what this means. And so today's talk, I'll try to provide a little bit of a background and foundation as to how we can interpret this. So how do we interpret this? We have to start by asking the big guy himself. So we have to ask Albert Einstein, could you tell us what your theory tells us about black holes? And he would say the following. And you look at this, by the way, it's the only equation in this talk, and I'll explain what it means in a moment. You seem a little bit mystified, but actually, in some ways, it's a beautifully elegant yet highly complex set of equations, which can be described as follows. So the left-hand side here, given by G, describes space-time. So this is Einstein's fundamental concept that space and time are not distinct entities like how we experience in our daily lives, but they're actually dimensions which should be treated on an equal footing and woven into this fabric. And so 4 dimensions exist together. And this is a quite profound concept. And the right-hand side of his equations describe matter. And so his equations are basically telling us that space-time, which is what matter lives in, so matter being stars, galaxies, dust, us, we live in space-time. And space-time is proportional to matter, and conversely matter to space-time. So there is a dynamical feedback. So in essence, it's saying that if there's a change in space-time and the structure, the fabric of the universe, then that will lead through proportionality to a change in the distribution of matter. But conversely, if there's a change in the distribution of matter, like if you make something more compact and dense, this will give rise to a change in the geometry of the space-time. So it's a very bizarre concept, but one which works very well in practice and has been verified experimentally time and again. So as one example, we can think about the deflection of light by a massive body like a star. And so the following image really is just showing what happens to starlight as it passes a massive object. So star B, the rightmost star, the light travels in a perfect straight line from that distant star to us here on Earth. But star A follows the curvature of the space-time around this massive object, this star, and you see it's slightly bent because it has to follow the straightest possible line in that curved space-time. And so this leads to a small correction, but that would change the apparent location of that star. And in fact, we do measure such deviations in starlight. And this is one of the first important predictions of his theory. And it's passed every test since. In fact, it's the cornerstone of a lot of modern technology. For example, GPS systems depend critically on Albert Einstein's notions of space-time. So anyway, moving on. So black holes are a prediction of Einstein's theory. They existed before as a notion, but they are a theoretical prediction that comes from solving these equations. And so we have to ask ourselves, okay, now we have a solution of his equations, a black hole. What is a black hole? What's going on around a black hole? What does it mean astrophysically? Well, the first thing is, let's look at a simple scenario. A black hole is characterized by an event horizon. And this event horizon is a region within which nothing can escape, not even light. So once you cross this threshold, you are doomed. You will never return, and communication with the outside world is impossible. So this is what we effectively define a black hole as. And within this event horizon exists a singularity. And this singularity is basically a problematic region within the equations which describe the black hole. And we're not happy as scientists with this. It's something we have to live with, but we understand that it's most likely due to an issue with general relativity itself being incomplete in various ways, which I don't have time to go into today, but it lives within the event horizon itself. So for all practical purposes, it doesn't affect us from an experimental point of view. So, but a black hole is black and it captures light. So how do we see it? And the answer is black holes are greedy and they like to feed on matter. So matter, which is unfortunate enough to get too close, ends up being dragged along with the black hole, which itself is rotating, and slowly falls inwards. And it forms an accretion disk. And this accretion disk, you can think of it as like water swirling down a plug hole, but just on a much grander scale. And the processes are very different. So as the matter is swirling around in the accretion disk, it's moving faster and faster as it gets closer to the event horizon. And there's a lot of friction and other dynamical processes which generate heat. And so this accretion disk becomes extremely hot and bright. And it's so luminous, in fact, that it radiates radiation across the entire electromagnetic spectrum. So from radio waves all the way up to X-rays and gamma rays. And so this radiation escapes, and to see the black hole, we would have to capture this. But before we can talk about how we would capture this radiation, this light which is produced, we first have to understand what happens to the light, because if you recall, the gravitational field of a black hole is so strong that nothing can escape, not even light. Then we need to first understand how light behaves around a black hole, because it doesn't travel in straight lines anymore. In fact, it can be severely warped. So if we're going to take an image of a black hole, we need to understand this. And finally, there is a relativistic jet, which is not relevant for today's discussion, but powerful magnetic fields mean that matter can be launched away from the black hole, both above, as you can see, and also below the plane of the accretion disk. So let's talk again about the dynamics of light. So what happens to light as it moves around a black hole? So in the center here we have the event horizon in red and a light ray which has just passed nearby. Now if a light ray passes even closer to the black hole, you can see it's more severely bent. Now let's increase the number of light rays and let's rotate our field of view. So you see space-time curving at the center there where the singularity is. If we go into a continuum limit and we fire more and more light rays, in the end we end up with a lot of radiation which we can collect on, for example, a CCD, like in a camera, and we can record an image. Now this is of course highly idealized because the black hole is not rotating, the distribution of light is isotropic, it's coming from everywhere, but you would end up, if this were the case, with a perfect black shadow and a bright halo. And so this ring-like feature, much like an eclipse, you see for example a solar eclipse, is what we expect to see from a black hole. This is one of the theoretical predictions. And in fact, what we do detect in the end is quite similar to this, but nature is not so simple. And the matter around a black hole is not distributed isotropically. We think it's more sort of a disk or toroidal geometry. So various scientists have tried to predict what would happen. And in fact, Hollywood has been amongst the predictors. And so you may have all seen the movie Interstellar in 2014, directed by Christopher Nolan. I'm sure many of you have. And during the film, they travel to a black hole called Gargantua, and they end up near the so-called accretion disk. And this is an image of the accretion disk. So this is a perfectly thin disk that's viewed edge on. And because of the bending of light by the gravity of the black hole, you see the rear side of the disk fold upwards and the underside of the disk fold downwards. So this is not a physical folding. This is just a bending of the light, you see. And so in that sense, the warping of the light is accurate. But in the sense of the physics of the flow of the matter itself and what we see, it's far from perfect. So it's uniformly bright, whereas actually the black hole is spinning, it's rotating in a sort of anti-clockwise sense. And so the left side should appear brighter because that material is moving towards us and it's Doppler boosted. And that right side should be conversely dimmed because it's moving away from us. So actually the first calculation which did this properly was by a chap called Jean-Pierre Luminet, and he did this in 1978. So he used computers at the time to calculate each of these points, and then each of these points was a calculation on some of the most powerful computers of his day, and he had to make these points on using India ink on photographic paper, and then take the negative of the negative in order to create the image that you see here. So it was actually it was a painstaking task and a labor of love, but you can see that actually it's pretty accurate. So he has the left side that's brighter, the right side is dimmer. You even see a sort of ring feature inside, that's light which orbits the black hole multiple times, that's lensed into a ring. So it's very impressive that this was done back then. But we've come a long way. And so the question then is, what can we do now? So here's an example of a calculation that I performed with collaborators. So this is a supercomputer simulation of how matter, which is magnetized, moves around a black hole. And in the movie, which I'll start now, we vary our observer inclination angle. So we fly to the north pole of the black hole. You see it's uniformly bright. Now we're in the equator and it's bright on one side. We move down to the south pole. And now we move towards the equator again and we see it's bright on the left side because it's spinning towards us. And now we fly around near the equatorial plane, near the equator. And you can just see the distribution of this matter. And it's neither optically thin nor optically thick. It's a sort of tenuous, turbulent accretion flow. And we think this is characteristic of how a real accretion disk would look in nature. So, okay, we have a background for the light itself. So how do we detect this in real life? So the following movie shows what happens when we let matter fall onto the black hole. So let's let it play. And after a time, turbulence develops and matter is forced to fall onto the black hole. And eventually the magnetic field in the matter winds. It coils up and it plows through material above and below the black hole, forming a jet. And if we zoom in and look closely at basically atomic processes which are happening in that matter, we'll see the following. So you see these blue vertical lines, these are magnetic field lines, and the yellow helical trajectory is an electron which is gyrating around these field lines. As electrons gyrate around the field lines, they emit radiation, red trajectory here, and it's this radiation that we detect, and in particular, the matter around black holes that we see using the Event Horizon Telescope produce copious amounts of radio waves. And radio waves in particular are useful because as for the same reason that we use them for communications here on Earth, radio waves can travel through the interstellar medium and even the intergalactic medium and reach us here on Earth relatively unattenuated. So they are very useful. And so what we have to do in the end is tune in a sense, to the black hole radio station. And the wavelength that we're looking at is 1.3 millimeters. So that's actually very long. You can see that. That's a very long radio wavelength, and that's it. That's the reason it needs to be so long, so it can reach us and we can make sense of it. So how are we going to detect these radio waves? So we need radio telescopes. Now, the problem is no single radio telescope here on Earth has the collecting area that's required to detect a black hole. So here is a radio telescope at the NRAO in the US, I believe Green Bank. And this is a pretty big telescope. Now, the problem with building pretty big telescopes is that sometimes this can happen. And so there are, above all else, engineering restrictions and limitations based on materials and so on to how large we can build a telescope. So we're obviously not going to achieve this by just building bigger and bigger telescopes. We need to think a little bit outside the box. So just for a sense of perspective, how high is the resolution that is needed to resolve a black hole, to resolve the event horizon itself? So let's think about the moon. So the moon has an angular diameter, roughly, a full moon, of around 30 arc minutes. So that's about half a degree on the sky. So it's pretty big. We can see it with the naked eye. Now, on the left here, I won't go through it, but you see an angular size scale. So M87, which is the black hole that was imaged by the Event Horizon Telescope, has a diameter of 40 micro arc seconds. So to scale, this is 1/90 millionth of a degree. So it's 45 million times smaller on the sky than the moon is, the full moon. And the Event Horizon Telescope actually has a resolution of half of this. So it's better still. So it's quite remarkable. So this is akin to, on a clear night here on Earth, at sea level, of being able to resolve with the naked eye an orange on the surface of the moon, or as some of my American colleagues like to say, read the New York Times from London with the naked eye that in New York, or to look at individual atoms within your own finger. So it's extremely high resolution. Now, a quick movie on how we do this. So you have to construct a telescope the size of the Earth. So it turns out that having a telescope of roughly the diameter of the Earth would provide the resolution needed to resolve this. So this is, in a sense, what we actually do. So when the radiation is produced by that black hole 55 million years ago, it goes on a long journey, and eventually it's received here on Earth, and it's detected at radio telescopes. But as you've seen, one single radio telescope isn't enough, and what we do instead is we employ a network of radio telescopes, and we link them using a process called very long baseline interferometry. Now, the radio signals produced by the black hole are detected here on Earth, and there are slight delays because of the different geographical locations of the receipt of that signal. And those precise arrival times are recorded using atomic clocks, which have an accuracy of better than 1 second in 100 million years. And so because we're able to record very precisely the arrival times, we can, in a sense, stitch together digitally the data recorded at each telescope and have an image with a resolution that's as high as a telescope with the same diameter as the largest distance between any two telescopes within that network. And this is effectively what the Event Horizon Telescope achieves. It constructs a radio telescope the size of the Earth. So the last few slides are just a little bit about what we can learn. So beyond simple speculative things. So one of the first things is the sense of scale of this image. So here's the image, and to scale, here is the sun, and here's the orbit of Pluto, which unfortunately is no longer a planet, but there we go. And here's Voyager 1, which began its journey in the late 70s, and has only just reached the edge of where the event horizon would be. And so this bright feature, which is the plasma, this accretion disk swirling around the black hole, it's bright because it's reaching us, and we've seen that now from the pictures and movies that we've looked at in today's talk. But we can do more. So not only is the black hole vast, absolutely enormous, it's bigger than our solar system, we can actually do a good job in constraining its mass and weighing it. And we find that it's around 6.5 billion times the mass of our sun, so absolutely enormous. But we actually have a nice constraint on the error of that, and it's less than plus or minus 1 billion. Now that doesn't sound like much, but actually that's a very good constraint for a black hole that's so far away. And previously this mass was quite uncertain. We also know what it is not. So we know it's not a wormhole because a wormhole would have a bright region which is much smaller, as shown here in green. And we see that there's variability in this image from day to day. So it changes actually quite rapidly, which is surprising because the black hole is so massive. Because of its size, we'd expect it to change on a timescale of maybe days to weeks. And instead we see variation from day to day, which is indicative of strong gravitational lensing. So it's indicative of light being bent and warped and distorted and lensed. And so this is fascinating because it means we're truly looking into a gravitational lens rather than just looking at a more mild vanilla kind of object which doesn't behave in this way. And finally, this, what we call the shadow, this bright ring, the size and shape of this shadow is very sensitive to the geometry, the structure of Einstein's space-time. So in the future, when we have better, more accurate measurements of this, we'll be able to test Einstein's theory of general relativity with even greater precision and in a regime which so far has never been tested, truly. And this is very exciting too. So I end with the following to say that, okay, we have an image, it's quite fuzzy, but it's a first step. And actually this is just the beginning. And in time, we'll achieve greater and greater resolutions, and we will look at other black holes too, and keep an eye out for some results later this year. We may see new black holes. And so with that, I just say thank you.